So this time we're going to be talking about heat exchangers. Now, heat exchangers are actually very similar to evaporators and condensers, in that all we have to worry about is heat transfer. So what a heat exchanger does is literally move heat from one substance to another. So we're going to have a hot substance losing heat to a cooler substance, which gains it. So let's just say we have a pipe of steam, and then it comes in contact with another pipe of liquid nitrogen. Now obviously steam is very, very hot, whereas liquid nitrogen is very, very cold. So heat's going to want to go from the water to the nitrogen. There's going to be a heat transfer here. So there's going to be a heat loss of the water. There's going to be a heat gain of nitrogen. Now these losses are going to be equal but opposite. We're going to assume that there's going to be no other ways for heat to be exchanged. Like these are well insulated, they're not going to go out or be absorbed by the pipes. So the heat transfer from here to here is going to be equal but opposite. So positive here, negative here, but they're still going to have the same absolute value. So what we could say is heat in plus heat out is 0. Conservation of energy. So Q in, which in this case is nitrogen, because it's getting a Q in, is going to equal the mass flow rate of nitrogen times H2 minus H1. Both these are of nitrogen. Then Q out, I always forget these little dots, H2O, in this case, not always, this Q out is going to be H2O, M dot H2O, H2 minus H1, H2O. Now notice, we have 6 different numbers here. We have mass flow rate of nitrogen, mass flow rate of H2O. These are 2 different flow rates. They are not flowing in the same pipe, so they can go at different rates. And then we have the state 1 and state 2 of both these substances. So we have 6 things to worry about here. So how would this look in practice? Well, let's say we have a big old heat exchanger. This is a pipe, cross-section of a pipe where there's refrigerant R134A going in and out. But as it's going through this part of the pipe, it's running over other pipes that are running perpendicular. So it's going into the piece of paper. More pipes. And in this is cooling water. So we have gaseous R134A running through these pipes, and then it's going to be flowing over cool pipes that has water flowing through it. And on the other side, it's going to come out as a liquid. So let's see. We have to give you a few knowns. We have for the refrigerant, we know that it has a mass flow rate of 1 kilogram per second. We know that at state 1, as it comes in, it has a pressure of 1 megapascal. We know that it has a temperature of 60 degrees Celsius. We know in state 2, it has a pressure of 887.6 kPa. We know it has a temperature of 35 degrees Celsius. And we also know that it is a liquid. And for water, So we know P1 is going to equal P2, which equals 2 megapascals. That's just something I gave you. Pressure doesn't have to stay the same. But since it's going to stay water throughout, it's a good assumption. And we know it goes from 20 degrees Celsius to 40 degrees Celsius. And what this problem's asking is find the mass flow rate of water. Alright, so we're going to use this equation, Q in plus Q out equals 0, conservation of energy. So Q in, that's going to be water. So Q in is just going to equal the mass flow rate of water times H2 of water minus H1 of water plus mass flow rate of the refrigerant times H2 minus H1. So we need to know all these enthalpies. Fairly straightforward, looking them straight up in the tables. We know H1 of the refrigerant at 1 megapascal and 60 degrees Celsius is 441.89 kilojoules per kilogram. And we know that H2 is a liquid, and at this state of pressure and temperature, it's somewhere along the saturation line. So we know that since we know it's liquid, we just take the liquid value from the table, which is 249.10 kilojoules per kilogram. For water at 2 megapascals, 20 degrees Celsius, that's super cool. You can look that up in the table. And we know that its enthalpy is 83.82 coming in, and at 4 degrees it's 167.29. So like before in the last video, we noticed a gain in the water because heat's coming into the water, and we notice a loss in the refrigerant because it's cooling down. So mass flow rate of water is going to equal mass flow rate of the refrigerant times H2 minus H1 over H2 minus H1, refrigerant, water. Plug and chug. So that equals 1 kilogram per second times equals 0. So there's actually going to be a negative sign there because we're going to have to subtract this over so we can divide. Going to equal 249.1 minus 441.89 all over 167.29 minus 83.82. Negative sign, which equals 2.31 kilograms a second.